distribution of velocities in a single direction, so thinking about, say, the x-axis, one thing that we're more often interested in is what's the speed distribution. Basically, how fast the particle is moving, irrespective of what direction they're moving in. And so remember to go from, when we're thinking about speed versus velocity, for speed, if we're thinking in 3 dimensions, we write that as u. That's going to be the magnitude of the velocity vector. And so if you remember to take a magnitude, we add up together all the squares of the different components, the x, y, and z components, and then take the square root. Essentially, this is like a Pythagorean theorem type deal. And so we can derive the speed distribution from the individual velocity distributions based on this relationship here. And that derivation is in your book. It's not that complicated. One thing we have to do is we have to switch to spherical coordinates. But we're just going to look at the final result. So the final result, the speed distribution, is similar but different than the velocity distribution. So the speed distribution is given by this function, f of u du is equal to 4 pi, that comes from the switch to spherical coordinates, times m over m being the molar mass, just like it was before, m over 2 pi RT raised to the 3/2 power, times the square of the speed in an exponential term. Negative molar mass times speed squared divided by 2 RT du. So this is our speed distribution. One thing to note about the speed distribution versus the velocity distribution is that here u can be equal 0 to positive infinity, but no negative values. Because we're talking about speeds, the idea of moving backwards or moving in the opposite direction doesn't mean anything because there's no direction associated with this. This is strictly for speed. Okay. Now, what can we do with the speed distribution? Well, number one, we can look at what does it look like? The velocity distribution looked like a Gaussian function. The speed distribution is mostly Gaussian, but because of this u squared term that we have here, it looks a little bit different. It's not symmetric anymore. For one thing, there are no negative values, right? So this doesn't extend past 0 here. And so we can see we have this asymmetric shape. So we have a longer tail here on the right at higher speeds compared to lower speeds, right? So there's an asymmetry here compared to the velocity distribution. We of course go to 0 at 0, right? There's no particles moving at 0 velocity, but everything, we get a long tail of things moving very quickly. So there's some interesting points that are marked here. This is an image I got from online, but these are points that I wanted to talk about anyway, which is perfect. So again, here's the velocity, the speed, not velocity, the speed distribution here. And we've already talked about this RMS speed, right? This is the root mean square. And we derived this formula earlier from the ideal gas law, right? So that the root mean square speed, if you want to remember that is, you take the square root of the mean of the square of the speed. And we can add a couple more because we know the distribution. So one is the most probable point, and this is the maximum of our distribution. So this is the most probable speed. And this one we can derive by taking the derivative of the distribution, setting it equal to 0 to find the maximum value, and then solving that for what's the speed that corresponds to that. So that's this point here, right on the very top of the curve. The other one we have is the actual average. And we can find this since we know the whole distribution. We won't go through the derivation, but we get this equation here, square root of 8 RT divided by pi times the molar mass. And you can see these are all fairly close to each other, but not quite the same. The most probable speed is the slowest of them. The mean speed's in the middle, and the root mean square speed is the largest. And that will be true no matter which gas you're looking at. One other thing we can think about is there are a couple of variables in here, particularly here in the exponential, right? Mass and temperature show up again, just like they did for the velocity distribution. And similar to the velocity distribution, these will affect the width of this overall distribution. So if we increase, say, the molar mass, for example, that will lead to increased molar mass leads to a decreased width to the distribution. right? So the heavier your molecules are, the more they'll clump together at around that most probable and average speeds. And the opposite is true, right? The lighter a particle is, the more this will spread out. And temperature will have the opposite effect, right? So if we increase temperature, that will lead to a increased width of our distribution. So the distribution will widen out. You'll have more particles moving at higher speed, and that's similar to what happens with the velocity distribution. So in the next video, we'll look at mathematically what else we can do with this distribution is look at what fraction of molecules are within given speeds. So say we want to know what fraction of molecules is right here, and you can see that's an area, and we're going to need to integrate.